Good morning. We are ready now to move on into chapter 23. The topics we're looking at here are electric potential and electric potential energy. So some of those concepts may be a little familiar. We've looked at gravitational potential energy, but let's see how this is related. Now, the earlier chapters, 21 and 22, we were looking at electric forces and electric fields. So this is kind of the rest of the story, is looking at the electric potential and potential energy. I'm going to jump through these list of topics and move to this first diagram. What we have here, there's a lot going on, so let me kind of organize this a bit. We've got two charged plates. Notice this one on the left is charged positive, this one on the right is charged negatively. There's a distance between them. Now, if we take a charge, let's say it's a positive charge. We always start with positive charges when we're discussing how these concepts work. And then we can switch and say, aha, what would happen if we switch to a negative charge? So we've got a positive charge, and it's at the positive plate. And then we're going to either allow that charge to move to the other side, or we're just going to let go of it. We could just let go of it and it would be pushed to the other side. What's going to happen in terms of potential energy? So let's see, if I let go of it on this side, it just kind of takes off all by itself. The positive charge on the plate will push that positive charge over to the other side, as well as the negative charge attracting it. So if I remember how potential energy works, that means that to bring the positive charge over here, that's like storing up some potential energy, and then by letting it get pushed back away from that positive plate, that would be releasing the potential energy, or let's say lowering the potential energy when it goes to the other side. So that's how we've got this labeled. We've got this labeled as, when the charge is on the left side, that must represent more potential energy. And we've got the units set up with that. So I'm looking at the units, and those potential energies are going to get measured in joules. If now the charge is moved to the other side, that's a lower region of potential energy. So if I follow the electric field, if I follow the force going from point A to point B, forces guide us towards regions of lower potential energy. Now we're going to introduce a new concept, and that is electric potential. Now you might think, well, potential energy, potential, aren't they the same thing? And they're not. I don't know whose idea was to name two things with such similar names, but electric potential energy and electric potential are two distinct physical quantities. Potential energy is measured in joules. That's the one that you're probably familiar with from the gravitational analogy. This new thing called electric potential, the symbol we use for that is a V, which doesn't seem very mnemonic, but the U didn't seem very mnemonic either. This has units of joules per coulomb, and it's actually, those are volts. Now, everybody's heard of volts, right? When you go and you buy a battery, or when you plug something in, you're always looking to see how many volts is this appliance, how many volts is this device. And volts are a measure of this new physical quantity, electric potential. So electric potential doesn't directly have to do with the force. Electric potential has to do with the electric field. So if the electric field in this diagram is directed from the left side to the right side, by definition we say that the electric potential is higher on the left side and lower on the right side. Now, saying that something is high potential or low, like high voltage or low voltage, that's a little bit misleading. You know, you might think, well, is high voltage dangerous and low voltage is safe? When we talk about high and low voltage as being safe or dangerous, that's in terms of how much voltage difference is there between the two plates. So we'll try and keep track of that. We'll find it's a bit arbitrary as to how we assign voltages for the two plates. But when we talk about danger high voltage, that's not saying this plate's more dangerous than this one. It's saying that the difference of voltage between the two plates is large. Okay, so let's move on from this. Here is how electric potential energy, measured in joules, is related to the electric potential. It's through a factor of the charge Q. And so here are the way that we can write the equations. Now, the unit of electric potential is a volt, and a volt is 1 joule per coulomb. And just like potential energy, electric potential allows us to assign at one location kind of an arbitrary 0 point, and then all of the other potentials are measured relative to that location. So again, in some sense, every time we talk about electric potential, it's really a difference. When we say that a battery is 12 volts, it's a difference between the two terminals. It's not saying one terminal on the battery is at 12 volts and one's at 0. It's saying that the difference between the two is 12. All right, let's go back to the fundamentals here. You know, everything that we did with electric forces started off by saying, hey, I got a couple of charges, they're separated by some distance. This picture is supposed to show center to center difference. Somebody got this diagram wrong. I should have corrected it. And we said that the electric force, you know, the formula here for the electric force looks pretty much like the formula for the gravitational force. In fact, it looks identical. They both depend on 1 over r squared. There's a force constant for each one of these. In the case of gravity, the force depends on the product of the two masses. In the electric force case, the force depends on the product of the two charges. So what that says is anything that we've developed for gravity is going to have a completely analogous set of formulas when we look at electric forces. So it actually provides us a chance to go back and do a bit of a review. Let's see, how does gravity work? Well, we started out by introducing what we called a gravitational field. So here's the gravitational field, and if we're near the surface of the Earth, that gravitational field is directed downwards towards the center of the Earth. And the units on a gravitational field are newtons per kilogram. Now, if you remember back to Physics 4a, at least if you were in Physics 4a in one of my classes, we started off with units of gravitational field of meters per second, but then we pretty quickly switched over into newtons per kilogram because of this equation. If we take an object with mass m, you know, here's object 1 with mass m1, here's object 2 with mass m2, we can find out how much gravitational force is acting on an object by multiplying the mass times the gravitational field. So if we put the masses in kilograms and the field in newtons per kilograms, that immediately gives us a force and tells us how much force will be acting. Now what we also did back in Physics 4a is for this particular case, this is kind of our simplest geometry, because in this case we're assuming that the gravitational field is uniform. It's close to the surface of the Earth, and it's over a short enough distance that we're going to be treating g as if it's constant. And if g is constant, then the force is constant, mg, and that says that we can define a gravitational potential energy formula as mgh. And I'm guessing a lot of you are going, yes, mgh, I remember that. mgh sounds familiar. That was on my formula sheet. So where this comes from is by taking the force and multiplying by a distance. That gives us units of energy. So if we have a gravitational force, mg, applied over a distance h, that corresponds to a potential energy of mgh. And kind of by definition, the higher potential energy is here, where the two objects have been pulled away from each other. the M1 and the planet, in this case the planet Earth, is the other object. So these two objects have been separated, and that's storing up potential energy. And then when we let them come back together, that's lowering the potential energy. Now, in the electric field case, we've got these two plates, one's positive, one's negative, and we're using that to generate an electric field. Now, we can't do much with the gravitational field because the whole planet's a really big object, but with electric fields, we can build devices and we can control the electric fields pretty readily. So a lot of our electronics, a lot of our electric devices have built-in plate that we can charge up and we can generate these electric fields. Now, when we generate these electric fields and we place charges within the electric field, those charges are going to have forces acting on them. In the gravitational case, that formula was mg. If we use the electric analogy, the force, the electric force acting on these charges in electric field E is going to be Q times E. So I put little vector signs over the fields, and I got the units on the electric field too. I think when you're drawing these analogies and trying to get an overview of everything going on, reminding yourself units at each step is really handy. The units, at this point you guys are building some intuition with units, and that says that when you see a set of units, it means something, or it should mean something, and it will help you keep everything straight. So we've done the same thing here. We've introduced some positive charges. These are not negative charges, but we've said that they'll have a certain potential energy. I can calculate the amount of potential energy by taking the force, QE, and multiplying by the distance. Now, just kind of through convention, when we're working with gravitational forces, those were typically vertical. We used h to measure those distances. With electric fields, we often use d. So I just wrote it that way. So mgh, which was gravitational potential energy, switches over into QED, quite easily done, when we're looking at electric potential energy. Now, what does happen if we get a negative charge inside here? What if the negative charges inside, Q1 or Q2, are negative? Well, the direction of potential energy switches. If it's a negative charge, then the higher potential energy would be on the right side and the lower potential energy to the left. So it just switches which side's lower and which side's higher. Now, it's worth reminding ourselves that this mgh represents the difference in potential energy from top to bottom, as well as over here, QED tells us how much additional potential energy is there on one side compared with the other. So these are just keeping track of differences. All right, so here is the whole package. Here is all of gravity condensed down into this one slide. The gravitational force in nature, we can start by defining a gravitational field and then saying that an object in a gravitational field will experience a force mg. There's something called the gravitational potential, which we didn't introduce in Physics 4a. Our textbook didn't introduce it. We didn't bother with it. But I'm going to put this in for completeness because I want to be able to draw the comparisons between electric force and gravitational force. And when we get to the electric force, we certainly want to introduce electric potential. Now, the symbol here is V, and the potential energy symbol is U, so that means that we use the same symbols for potential energy both in the gravitational case and the electric case, and we use the same symbol for potential. The potential comes from integrating along the gravitational field. So if I start at this higher location, and I follow the gravitational field, and I multiply it by distance, that little ds means that I'm going to take one little step at a time along this gravitational field. That will tell me by how much the electric potential is dropping. There's a minus sign out front, which says that if I follow the gravitational field, the potential will be dropping. Now, what would happen if I reverse direction? What if my path of integration, defined by these little steps of ds, if my ds's are in the vertical direction, that dot product is telling me that I'm actually building up potential energy rather than decreasing potential energy. So by reversing the direction of the ds, that dot product now has a cosine of 180. The gravitational field is still downwards, but the ds is upwards. And that says that I can drop in gravitational potential. I can switch and go back up in gravitational potential. What happens if I go sideways? What if I'm following a path defined by ds, and it's going sideways through the gravitational field? Well, then the potential is not changing, because two vectors that, gravitational field is down, that vector, ds is sideways. I only see differences in electric potential if I'm following the field downwards or following the field upwards. If I stay at the very same elevation, that's what's considered an equipotential surface. The potential is not changing. Now, to take potential and turn it into potential energy, what we did is replace the field with the gravitational force and then carried out the very same calculations. So the only difference between field and force is a factor of m. The only difference between potential and potential energy is that factor of m. So that's what gravity looks like. Let's try out some of these formulas. Let's say we have an object, it's 40 kilograms. Let's just, to make the calculations a little easier, let's say the gravitational field is 10 newtons per kilogram. So it's not quite the same as Earth. This is a Earth prime. This is a modified Earth with a gravitational field that's a little larger. I can easily then calculate the gravitational force on my 40 kilogram object. It's going to have a gravitational force of 400 newtons. So I'm going to have a gravitational force of 400 newtons. It's going to be down, directed in the downwards direction. Now, in the case, and that's my force equation here, in the case where the gravitational field is constant, I can calculate the gravitational potential by taking g times h. And I can calculate a potential energy by taking m times v, which is the same thing as mgh. So one way to think of this gravitational potential is the potential includes the field and the distance, but it doesn't tell us what mass object we're bringing in. So here are the formulas that relate field and force, and the ones that relate potential and electric potential, potential and potential energy. The F and the G are vectors. I guess I should have put some vector signs on them. But the potential and the potential energy are scalars. Okay. And then I did this. I said, okay, let's imagine a gravitational field of 10 newtons per kilogram. If I started at a height of 0 meters, and then I climbed 10 meters, and then 20, and then 30, what's happening to my gravitational potential? And if I follow the formula GH, that becomes 100 joules per kilogram, 200 joules per kilogram, 300 joules per kilogram. And then if I put an object, a 40 kilogram object in, I can calculate how much potential energy. So a potential of 100 joules per kilogram multiplied by a mass of 40 kilograms gives me 4,000 joules. So you can think of, this gravitational potential as kind of getting everything ready to bring an object in and measure its potential energy. I don't need to know the mass of what object is coming in order to calculate this, but I do to calculate the potential energy. All right, here's something with a little more detail in it. What we can also say is, here are those same levels that we've defined. I hope the numbers are the same here. Yeah, 4,000, 8,000, 12,000 joules. So kind of the same diagram as the last one. But this time what we're doing is we're saying, okay, what's another way I could think about potential energy? And one way I could think about potential energy is to say, well, let's get a cable and lift this object. It'll have tension in the cable. Let's lift it up 10 meters and then to 20 meters and then to a 30-meter height. How is the work that I'm performing, how is that related to the potential energy? And it turns out that the work is the force integrated over the distance. And in the case of the tension, lifting this object 30 meters, that works out to be 12,000 joules of work that we would have to perform. Remember, work is a transfer of energy using forces. And if I were to lift this object, this 40 kilogram object, to a height of 30 meters in a gravitational field of 10 newtons per kilogram, that's going to require me to do 12,000 joules of work. And you go, oh, that's the amount of potential energy. That's one way of thinking about potential energy is if I have gravitational forces which are attractive, if I lift the object up, the amount of work required to lift the object to that larger height will equal the amount of potential energy that we've stored. Now, at the same time we're lifting with tension T, gravitational force is pulling downwards. So what we already did is talk about how much work we're doing by lifting this object. What's gravity doing? Now, gravity in this case, the work done by gravity as we lift something up, gravitational force is in the opposite direction of the little ds's that we're taking. And so I get a minus sign here. It says that when I was putting 12,000 joules of work in to the system, the gravitational force was taking it out. And if the forces match, if we pull with just enough tension to offset mg, then we'll end up putting 12,000 joules in, gravity will take 12,000 joules out and store it as potential energy. So that's how the story is told about how's energy conservation, how is that managed in this example that we are looking at. All right, so this is a really detailed example. And so this is lifting it up. This is one that we just looked at where the ds's are headed upwards and we're lifting at a constant velocity. We matched the tension with 400 newtons. The gravitational force is 400 newtons. That's going to enable us to lift this object at a constant velocity. When we calculate the work done, we have put in 12,000 joules of work by attaching the cable and lifting this up by a motor or something. The gravitational force has removed 12,000 joules, and that means the object itself, for this particular setup, it doesn't acquire any kinetic energy. Because the energy taken out by the gravitational force balances the energy we put in, there's no net work, and the kinetic energy will remain fixed. It will remain constant. Now, we can calculate the increase in potential energy by looking at the work that we put in, by integrating our force over that distance. Another way to calculate the potential energy is to say the increase in potential energy is the work that was the energy or the work taken out by the gravitational force. So whenever the gravitational force is opposing the displacement, that's removing energy. Now I put the minus sign in, and that says that, whichever way we calculate this, it's 12,000 joules of potential energy that we've built up. So that was when we were lifting the object up. What happens when we lower the object? Well, we could still lower it at a constant velocity. The ds's are now in the opposite direction. Now, since the displacement is downwards, that says it's the gravitational force that is now transferring energy in. The work done by the gravitational force will now be positive 12,000 joules. Uh-oh, somebody left their units out. Joules here, joules there. This time it's the tension in our cable that are taking out 12,000 joules, joules. So again, I can follow this formula right here. What happens this time is that, strictly speaking, that negative sign shouldn't be there because the negative sign's coming from the dot product. So maybe cross that one out. This one looks, I guess that doesn't, it's a negative value, so I guess that's what we wanted. Oh no, I'm sorry, it is there. It's the gravitational force we're looking at. I take it all back, keep that in there. The minus signs need to cancel. There's two minus signs and they'll cancel and become a positive number. All right, sorry about that. So the last example, so in this case, both keeping track of the work that we've done or keeping track of the work done by the gravitational force says that, and following these formulas, tells us that we've had a reduction in potential energy. And then finally this last diagram, which is everybody's favorite, is where you just drop it, right? You go, oh, forget with this cable, let's just drop the object. If we drop it from point A and let it drop to point B, and it follows all of these DS's, that says that the work done by gravity is plus 12,000 joules. That means that the potential energy will decrease by 12,000 joules. There is no tension force. We didn't have a cable. We cut the cable. Cable's cut now. And so we're getting 12,000 joules out of the gravitational field, and that's going into the object. And as a result, the kinetic energy that the object acquires is going to be 12,000 joules. So we can do an energy conservation calculation here and find out how much kinetic energy the object will acquire by the time it has dropped through the 30 meters. So I hope this is all familiar. Now, what we want to do is take everything we've said here and on these last couple of slides and replace it with the electric force and the electric field and with charges. So everything we've said here works the very same way with the electric force. So there's a field, which is the electric field. There's a force acting on charges that enter the field. So here is a charge entering the field, and it's going to have a force of Q times E acting on it. Now, if it's a positive charge or a negative charge, either one, the direction of the electric field will guide us away from higher electric potential towards lower numerical values. But again, remember, the important quantity here is the difference between the two numbers. We can use these integrations. We can integrate along the path of the electric field to find out the potential. We can multiply that by a charge to find out how much potential energy difference that represents. Okay, so here's a diagram. I hope it looks kind of like the other one. Notice that when we're doing these electric force calculations, typically we ignore gravity. We tend not to do both at the same time, unless a homework problem or a midterm problem specifically says include both electric and gravitational effects. Typically, in this chapter, we're just looking for the electric calculations. So here I just picked up, I picked a random number for a charge, 5 coulombs, random number for an electric field, 20 newtons per coulomb. 5 coulombs is a lot of charge. 20 newtons per coulomb. And I assume that the electric field was constant. For that, the electric potential can be calculated times E times D, and the potential energy can be calculated by Q times E times D. Now in this case, in my D column, I've got the 10, 20, 30 meters. If the electric field is directed downwards, that says I've got a region of positive charge up here and a region of negative charge down here. That's setting up that electric field. And what that's going to do is it's going to take positive charges and push them in this direction, but it's going to take negative charges and push them back the other way. Once we have designated the direction of the electric field, that tells us how much voltage difference we will have. But when we move on to the potential energy, the potential energies are going to be Q times V. For positive charge, changes in potential energy and potential are in the same direction. But for a negative charge, the direction of the force reverses and the direction of potential energies reverse. So in this case, I've decided to start at the top for the negative charge. Decided to start at the top and call that 0 joules, and then work my way back down. Okay. Another way I could have done this is set minus 3,000, minus 2,000, minus 1,000, and 0. So we could have done that also for those potential energies. All right, we're getting back. This looks kind of like that slide that we started with way back before we did all these gravitation and electric analogies. This is our first example in the chapter. It says that we have a negative charge, and we want to take that negative charge and place it in a region where there's an electric field. Now, what I'm hoping you're starting to see here in these examples that we're looking at is there's really two sets of charges going on here. There are the charges in the plates, which were initially set up. So I've got some I got some plates. I set them up, I connect some wires, I put them to a voltage source, to a battery, something like that. And what I'm going to do is I'm going to set up an electric field by using a battery, for example, and charging one of the plates to be positive and charging the other plate to be negative. So that's going to set up a group of charges on those plates. Now, the presence of those charges are going to generate an electric field. And from last chapter, chapter 22, when we were looking at Gauss's law kind of hinted at the idea that if we get two pretty good sized plates and place them close enough to each other, the electric field between them becomes reasonably uniform, reasonably constant, and so we can tell ourselves that we are generating an electric field that's uniform. Now, in chapter 22, in our lectures, we actually went through and showed that that's really kind of an approximation. We have to get these plates really close to each other in order to maintain a uniform electric field across that region between the two plates. So that's kind of our standard diagram for setting things up. It usually takes more effort. There's some items that we do have to make sure are taken care of in order to set up a uniform electric field. All right, in this case, what we're going to say is that this plate is negative, this plate is positive. Now, that says that the electric field is directed from left to right, and remember, that was just arbitrary. We could have defined positive and negative charges oppositely to the way they were defined. So the direction of these arrows doesn't really tell us. It could have switched. It could have been defined the other way around. Now, because these are negative charges, placing a negative charge, this is the other charge that comes in. So we got these plates set up. They've already been charged, and then we wait around until another charge comes by. And here is that other charge that's coming by, and it's getting placed at the negative plate. Well, it's going to get pushed away from there. Negative charges are going to experience forces in the opposite direction to the field. Now, since the force is back in the other way, this is the high end, this is the high potential energy region, and over here would be low potential energy. Even though, in terms of just electric potential, this continues to be the low potential and this high. So what it says is this. It says that U and V match up for positive charges, but if it's a negative charge, the high potential energy will be at the lower potential location. And so here it is. Here are the diagrams. Here are the plates. I should have not brought the charge in. Let me remove that charge for a minute. VB, by definition, is higher and VA is a lower quantity. So for example, we could, if we're using, did they bring up 100 volts? I brought up 100 volts. Okay. Okay, I thought they, but anyway, so I set up 100 volts difference, so I got a voltage source, a lot of batteries or something, and set up a 100 volt difference between those two plates. They're separated by distance d, so that there's a difference of 100 volts between the two plates. VA I called the 0 volt and B I called 100. I could switch those. I could call this 0 and then this would be negative 100. But in any case, VB is defined to be the higher quantity and VA to be the lower quantity. If we have a negative charge that is moving through this region, then the B side is going to be lower in potential energy and the A side is going to be higher. Now, if I wanted to calculate some numbers, and that's, I guess, why I put in these voltages, if this is an electron, which they tell us it is, the electron's going to have a charge of 1.6 10 to the minus 19 coulombs. That's the charge on an electron. And so what I can do with these formulas is I can keep the plus and minus signs. Remember back when we were looking at forces and electric fields, forces and electric fields were vector quantities. And we said that if we were setting up a bunch of charged objects and calculating the forces and calculating the fields, usually we use the diagram to keep track of directions, and in the formulas we just treated everything in terms of its magnitude. So we really didn't pay attention to plus and minus except in the diagrams, not so much in the calculations. With the scalar quantities, when we get to electric potential and electric potential energy, which we've gotten to, these are scalar quantities, and the formulas here work really well if we keep the plus and minus signs in. So that's what I'm going to do. I'm going to keep the minus sign in on that Q, and that says that if the potential difference is 100 volts positive, then the potential energy difference will be negative 160 times 10 to the minus 17 joules, and that's just a reminder of how potential energy will work for negative charges. The differences are going to be reversed. All right, as long as we're talking about voltage, this wasn't included in the chapter in our textbook, but I thought this would be a really handy time to talk a little bit about batteries. You know, this is, here's a battery, here is a wire that I've attached to the positive terminal. I ran it over, here's a light bulb, and I connected to the light bulb here, and then I took another wire and connected to the opposite side of the light bulb and ran that back. So I have a closed path now of conducting material. Now, a closed path of conductors means that if I can get a way to push the electrons, because the electrons are mobile in these pieces of metal, if I can get a way to push the electrons through here, I can generate what we consider an electric circuit, something where the electrons have a closed path. I really can't build up electrons appreciably in this circuit. There's nothing in this circuit that's storing electrons for me. What there is there's a battery, and the battery is pumping the electrons. So there's a chemical reaction going on inside here. I got those little F's, or the capital F's, that represent a force. The chemical reactants are set up inside my battery in a way where electrons in chemical reactions are getting pumped into the negative terminal region and away from the positive terminal. That's what makes the negative terminal negative and the positive terminal positive. Here I have a depletion of electrons. Here I have an excess of electrons. Now, for a battery that's just sitting there on the shelf, that doesn't happen very long. You get a little bit of negative charge buildup, a little bit of positive, and the electrons are really repelling each other And that means we're not going to build up an appreciable number of electrons. But what happens when we take a wire that's conducting, a piece of copper or something? Well, the electrons now have a path. So as that battery is pumping the electrons can get pushed through the circuit. Now, I don't have to wait for an electron leaving the negative terminal to travel all the way and return to the positive terminal, because everywhere in that wire, there are already electrons. So if you think of this as kind of plumbing, you could think of this as a bunch of pipes, and the pipes are all filled with water throughout. When we turn on the water pump, water begins getting pushed here, but this water has other water in its way. So this water is going to push against water that was already here, and already here, and here, and here. So water everywhere will start to move. When we turn that pump on, the water in the entire circuit of pipes begins to move, and we're going to say almost instantaneously that happens. That's what happens in electric circuits. So I've already got electrons here. I have electrons over here in this light bulb, in that filament. As soon as I close the switch, which I should have put a switch in here, as soon as I close the switch, those electrons are going to start moving through that light bulb, and the light bulb lights up. So again, I don't have to wait until electrons from the battery reach the light bulb, because there's already a bunch of electrons waiting. They're already just milling around in the circuit, waiting for somebody to close that switch. And then immediately they start moving at all locations. So using what we've talked about with potential energy and potential, if I have a battery with an electric potential of 12 volts, then what we can do is define one of the terminals. I'll define the negative terminal to be 0 and the positive terminal to be 12 volts. Well, an electron has a charge of negative E, minus 1.6, 10 to the minus 19. That says that the electron starting off at the negative terminal, we're going to define that as 0 joules. And then by the time it has gone all the way around, it will have been reduced down to negative 1.92 10 to the minus 18th joules. That's a difference of energy of 1.92 10 to the minus 18 joules. That's how much energy the battery provided just in that one electron. So by having one electron leave the battery and another electron arrive, that corresponds to an energy difference of 1.92 10 to the minus 18 joules. So that's how battery energy gets transported through our electric circuit. Now there's a couple different energy units we can use here. We can use joules, which is what we've done up here. There are also these other units called EV, which we'll see some examples of using these. If I'm using these units of EV, then instead of saying that the electron has a charge of negative 1.60, 10 to the minus 19 coulombs, I can say that an electron has a charge of 1 E, where E is a fundamental unit of charge. And that becomes part of my unit. So by the time the electron has gone around the circuit, that represents 12 EV of energy. So 12 EV is the same thing as 1.92 10 to the minus 18 joules. All right, we're back to this picture again, and so I hope we've made some headway here in terms of defining gravitational potential energy, electric potential energy. These formulas are a simpler set of formulas because we've assumed in this gravitational case that the gravitational field was uniform, G is a constant, and over here we assumed that the electric field was uniform, that the electric field was a constant. Now in terms of voltages, so we've got these units of volts now, there's this table from the textbook talking about a number of volts You know, an automobile battery, 12 volts, a flashlight battery, 1.5. A household outlet is 120 volts. Automobile ignition, 10,000 volts. So you can kind of see these different values for electric potential. All right, let's try another one of these examples. We still are using the parallel plates, positive and negative charge. We're going to take an electron, we're going to generate an electron beam. Now what they're calling this is a CRT, a cathode ray tube, but basically what these things are, a positive and negative plate inside a vacuum region. So I need to take all the air out and create a region in which the electron can move freely. It's not going to bump into some nitrogen molecule, for example. So I'm going to generate some electron. What we can do is we can heat up one of the plates, and actually by heating up the plates and applying a voltage, and in this case we have this 5,000 volts high voltage power supply that we've hooked up to, the electrons can separate from the plate. Once an electron separates, it now is going to get pushed away from that negatively charged plate. So the electric potential is directly given in this problem. That's our starting point, is to say that we've used 5,000 volts of electric potential set up between these plates. Now, what they want to find out is what's happening in terms of potential energy for the electron, and how fast will the electron be traveling once it gets to plate B. Now, notice, once it gets to plate B, it's going to accelerate. It's going to be picking up speed all the way because we cleared out all the air molecules. It's a vacuum region. So the electron just steadily it's going faster and faster. It's got this constant acceleration that's taking place. The speed is picking up. Now, when it gets to the other plate, there's a hole that we made, and that means that the electron passes through that. It's going really fast. It can't stop. And that means that we're going to generate an electron beam. So here's the plate A, here's the plate B, here's the electron. There was a little hole right there. And what's going to happen is once the electron exits, it's going to be traveling at some speed. And that's how we generate beams of electrons. X-ray machines, for example, start off with a beam of electrons. They speed them up to these high speeds and then run them into materials and generate X-rays. So these are handy devices. We use these in a lot of different situations. Now, if we think in terms of what's happening in terms of the electric field, notice that the electric field on my plates are directed towards the left, but the force on the electron is directed to the right. So we're looking at some number of these examples that involve negative charges, electrons. First of all, because electrons are very commonly used in these applications. Proton beams are not as common. Electron beams are easier to generate. It's much easier to get a bunch of electrons generated into a beam. But what that allows us to do then is show that in the case where the moving charge here is negative, the force is in the opposite direction of the electric field. What that says is regions of higher and lower electric potential are oriented oppositely to the regions of lower and higher potential energy. So the electron's going to start off with more potential energy and end up with less. So I did this little graph here and said that as we travel from point A to point B, now this is not in terms of time, but it's in terms of location. So in traveling from point A to point B, location by location, the potential energy is steadily decreasing, and we're thinking of this as, well, once it exits, potential energy is gone. We used up all the potential energy. Now, meanwhile, as it travels between the two plates, the kinetic energy is steadily increasing. So I've got this steady conversion from potential energy into kinetic energy. And then once the electron exits that region where the electric field is, the forces stop and the kinetic energy remains constant. So now I have a beam of electrons drifting through this vacuum region at a constant speed. So let's see how we could do this. We could do this with potential and kinetic energies using energy conservation. So energy conservation was a big deal back in Physics 4A, I guess in chapters 7 and 8. We did a lot of examples with that. And now we're going to be doing an electrical version of this. The potential energy that we start with at point A is 5,000 eV, which is the same thing as 8 times 10 to the minus 16 joules. Now, we got to do this problem in joules because eventually we want to put some masses in kilograms and such. So let me go ahead and switch over into joules. Let's say that we start the electron at rest. So we bring the electron to that negative plate, it's at rest, and then we let go. So we let go of the electron. It starts off with no kinetic energy, but by the time it reaches the other plate, the 5,000 eV, or the 8 times 10 to the minus 16 joules, has been all used up. So that leaves us with no potential energy. Everything has been converted to kinetic. So the difference in potential energies between the two plates tells us how much kinetic energy the electron will have as it exits. Now I can go back to Physics 4A and write down formulas for kinetic energies, 1/2 mv squared. Solve for V. When I did that, put all the numbers in. Now notice this is in standard units. So the kinetic energy needs to be in joules. The masses need to be in kilograms. And that's why I put in the mass of the electron. So that's a number that's going to show up from time to time through the rest of this course for sure, and all through Physics 4C. That's the mass on an electron. When I calculated that number, it says that this 5,000 volts that we set up between the two plates is enough to get the electrons moving 4.19, 10 to the 7th. That's like 42 million meters per second. That's really fast, right? Back in Physics 4A, we just didn't have speeds like this. But when you're generating beams of electrons or protons or whatever, we do have particles moving at these really, really high speeds. Now, another thing we could point out here is we worked entirely from the electric potential. All they needed to tell us was the 5,000 volt number. That was enough. Once we knew the 5,000 volt number, we could calculate potential energies. Once we knew potential energies, we could calculate kinetic energies. Once we knew kinetic energies and mass, we could calculate speeds. What didn't we have to know? They didn't have to tell us the electric field. And they didn't have to tell us the distance over which this was accelerated. It turns out that if they had told us the electric field and the distance, we could have used those, but the voltage becomes a shortcut. So it says, look, it doesn't really depend on how much distance there is between these two plates. I could put them close together, I could put them far apart. It really comes down to what voltage we place on those plates. If those plates have 5,000 volts on them, when the electrons exit, they're going to be traveling at 4.19 10 to the 7th meters per second. Now, if we put the plates a little farther away from each other, the electric fields will not be as large, but they'll be acting over a longer distance. The electrons won't pick up speed as fast. If we put the plates closer together, the electric field's going to be more extreme, and the forces will be larger, and the electrons will pick up speed faster. Now, another thing that's going to keep coming up for us when we're looking at these electric and magnetic forces is that when we do have electron beams or whatever, it's kind of fun to compare this to the speed of light. It turns out that the way space and time are put together, there's no such thing as going faster than the speed of light. It also turns out that the formulas we learned in Physics 4A are only accurate at speeds probably, let's say, less than 10%. So once we get past about 10% of the speed of light, we're going to start noticing divergences between reality, which is called special relativity, and kind of the classical approximation. So these electrons are already, with a 5,000 volt boost, they've got a high enough speed, they're traveling at 14% of the speed of light. And to get a better number here, we're going to have to come back in Physics 4C and explore some, we're going to have to learn about some formulas that are going to continue to give us the correct answer. So anyway, these electrons are starting to go pretty fast with a 5,000 volt boost. Now, it's worth asking, how would everything change if instead of an electron beam, what if it had been a proton beam? How would that have changed things? Now, if this had been a proton, the first thing we would have to do is flip the two plates oppositely in order to get the electron to accelerate, right? So we'll flip the two plates. We could still use the 5,000 volts. The potential and kinetic energies would work the same way. The protons would be traveling from left to right and go through that opening. Everything looks the same until we get up to velocity calculations, because the mass of the proton is going to be 1,800 times more than the mass of the electron. And what that tells us is that the mass of the proton, because it's so much larger, is going to result in a much lower speed. Now there is a square root sign here, but you know, the proton's going to be traveling 1/50th or 1/40th, something like that, maybe closer to 1/40th, the speed of an electron if we use the same voltage. And that's all related to the mass of the proton compared with the electron. All right, here is a diagram from the book showing that what happens if the electric field is not constant. What happens if I have electric field lines that are stronger, say at point A, and not as strong at point B? And what if I pick a random path? I don't follow the electric field line. Well, this formula that we've defined in terms of the electric force integrated along some path, dl, it works. So as long as there's some kind of formula, as long as I can come up with a formula that tells me how large is the electric field and what is the path determined by, I can calculate a force, plug that in, and we can continue to calculate differences in potential energy. Okay, and we'll see some examples of different geometries. Okay, here is a reminder of the simplest case. Things are going to get more complicated. So, you know, enjoy this in these first few examples where we have a uniform electric field and it's easy enough to calculate potential energies and forces, or come up with formulas, between potential energy and force and between potential and electric field. So we can kind of switch back and forth if these formulas work, if the electric field is uniform. Okay. And here we've got, so far so good. This is still one of those electric field, constant electric field examples. What's the electric field going to be in this example? We've got 50 volts set up between the two plates, and we've got a distance of 5.0 centimeters. Now, before I was saying some of these distances need to be center to center. Here, the distances and the voltages are set up just exactly right. What's going to happen on these conducting plates is the charge is all going to be along that inner surface. So the charge will be lined up on the inner surface here on the positive side, same thing on the negative side. The distance over which the electric field is going to get measured is just the distance between the plates. It doesn't extend into the plates themselves. Once I get into the conductor, the electric field will be zero. So the non-zero electric field is just from the surface of one plate over to surface of the other plate. Well, let's take a look at calculating this. Oh, great. Okay, so I didn't quite get that lined up. That needs to be on the edge. 50 volts. Distance is 5 centimeters. I'm going to convert that into meters. Now the electric field we were told in that for a uniform electric field could be calculated as V over D, that's 50 volts over 0.050 meters, and my calculator gave me 1,000 volts per meter. So that's an alternate set of units for the electric field, which works absolutely fine. It turns out that volts per meter are the same thing as newtons per coulomb. If we take a volt, which we defined as a joule per coulomb, and then separate the joules into newtons times meters. I'm trying to find the path here that I'm hoping is most familiar to all of you. What I've done is taken volts and written that as newtons times meters over coulomb. I can now bring the meters to the left side and place it in the denominator, and sure enough, volts per meter is the same thing as newtons per coulomb. So this is in terms of potential per distance, and that's in terms of force per charge. So between these two plates, if it's a 50 volt difference between the two plates, we could think of this as breaking down into a series of what we call equipotential surfaces. Now there's a lab coming up, I think, which looks at electric potential surfaces. So we got a couple plates here. There's a 50 volt distance. If this inner surface of this plate is defined, let's use that as a reference. As I move from one side to the other, the potential goes up. So, and for a uniform electric field, the separation between that is going to be evenly spaced. So what we're seeing in this particular example is each centimeter that I travel through that region corresponds to an increase or decrease of 10 volts. So practice with these drawings, these pictures, keeping track of how voltage varies. All right, the easy problems are over with. Let's look at some more difficult examples. We're going to start off with a spherical example. Now, for better or worse, maybe I should apologize for going back and doing all these gravitational problems. Here is my reasoning, my justification. You guys already sort of understand, maybe really well understand, gravitational potential energies and potentials and forces. And so by drawing these analogies, anytime we solve a gravitational problem, there's an analogous electric force problem that we could set up, and vice versa. So that means it's a chance to learn, to review what you guys already have learned about gravitational forces and gravitational fields. So it's a chance, it's a 2-for-1. So instead of just looking exclusively at electric forces, we can kind of switch back and forth between these examples, all the time telling ourselves, hey, if I can do a gravitational problem, I can do an electric force problem. So here's the deal. Let's say that here is planet Earth, and it's got a mass, a big M, and it's got a radius of big R. And what we're going to do is we're going to take an object from the surface of mass little m, and we're going to lift it off the surface. Now, I'm unfortunately blasting these things off with rockets. It's not the easiest way to think about what's happening. So let's imagine we have a new propulsion system, and the new propulsion system takes the object, I just placed the object on the ground, that's mass m, maybe it's a spacecraft, and the spacecraft just takes off. And it just keeps moving at constant, kind of like a flying saucer. So the flying saucer takes off, and it just keeps moving at constant speed, and it goes through the atmosphere and into space, and it just keeps moving at a constant speed the whole time. Now, how much work are the engines going to have to do? You go, well, the amount of work that the engines have to produce would match any increase in potential energy. So let's calculate the increase in potential energy as the work required from the engines. So this new propulsion system is maintaining a force, and I want to find out how much the potential energy is going to increase as I move away from Earth. Now to do that, I can take this force and integrate it with the path, as long as I stay on a path leading directly away from the surface of the Earth, I can write that as F times dr, and I can drop the vector signs. Now, we said we wanted to move away from the Earth at a constant speed. And that says that this force has to start off being a bigger force, because initially the force of gravity is going to be gmm over r squared. Here's my gravitational field. And that says that the force initially that we're pulling with needs to be bigger, but as I get farther away, the gravitational force from the planet, it's going to drop off. So the force that we pull with in our propulsion system is going to exactly balance out the gravitational force, so we have a nice constant velocity ride. So gmm over r squared, and I can integrate that along the path, and that will tell me, as we move away from Earth, at what rate the potential energy is increasing. So I've carried out that integration, and I've looked at the limits of integration. I'm starting not at zero. I'm starting already at the surface of the planet. So I'm starting at a distance of r from the center. In these formulas, the r's are always measured from the center of the sphere. And then I'm going to travel all the way out to some variable little r. Now, when I carried out the integration, I got this, and I'm hoping this looks familiar. This was our general formula for gravitational potential energy. I should take that back. It's not completely general. Let's say what this works for. This works anytime I'm looking at gravitational potential energies outside a spherical distribution of mass. So that means outside of a planet, outside of a star, outside of a black hole. If I'm far enough away, the potential energy is going to be given by this expression. If the space-time continuum is not too distorted, we can use classical formulas for that. So this looks like my potential energy terms. And potential energy at point B is minus gmm over r. Potential energy at the surface is minus gmm over r. And I'm taking the difference between two negative numbers, and that always makes me a little nervous. I have a fairly high failure rate once I get lots and lots of minus signs floating around in my formulas. And you guys know this from Physics 4a when we looked at these kind of problems. It takes one additional look at the problem to be really clear about how I'm going to keep track of these negative values. These values are always negative for gravity, because gravity is an attractive force, and for attractive forces the potential energies are defined to be negative. Now this turns out to be a good place to stop for the day, so I'm going to stop right there, and we'll pick up with this example looking ahead at the next class.